spike. So
Made it go like.
if your velocity does that maneuver right there, so you go from positive to zero, so you're losing it, then your acceleration, you know, spike down. something like
Okay,
that.
that's how you want it.
Yeah.
Oh.
Officially, it's infinitely long down, but you know, just some indication of.
So would a hole work?
I don't think it's conveying the same information.
So I can do that?
The-
That was the only thing I could figure out.
Yeah.
And then, so I accidentally ended up making it like a little spike so you can see the gap.
Oh, so you did, you know, a wedge like that?
Yeah.
Realistically, I mean, if this were actually, if you were doing this in front of a motion detector, this is more like it would look like. Well, actually, what it would look like would be. But yeah, it's, you know, it does, every 50th of a second, it's picking a position, so it's not instantaneous. Even though that might look instantaneous, in reality, you will not do it instantaneously, or your hand would, I think, splat
If it did.
if it experienced that acceleration. Probably your arm along with it.
Okay, so with the, like if the velocity changes like that, would you want us to write a line in the middle, like down from it?
So if your position graph, say that position graph?
Yes, yeah.
So, yeah,
You do on a line?
yeah, if you, on this one right here, if you don't do a line, you know, I can live with that. But for acceleration, I do want some indication of
Going in the direction.
going down or going up, whichever way it is.
So if you go from, and the spike is also in which direction you're accelerating.
Right.
Or which perspective from velocity.
Yeah. Which is one of the reasons why I want the spike in there, because it is also hopefully reinforcing the idea of the direction of acceleration. Any other questions? Apparently this does not want to come up.
Will you be available like after class for questions? I don't wanna like hold you up right now, but I do have questions about this now that they've reminded me of it.
Yeah, you don't want to ask the entire class in front of everyone, or?
Well, I will, actually, I'll ask this. On number 10 for the linear motion lab, where it's like, you have to describe an action
Right.
and make all this, how do you find the, what is it called?
Instantaneous displacement?
Yeah, that.
Well, it depends on your action, but the,
No.
because again, default language is displacement is overall displacement unless I say otherwise.
Yeah.
Velocity is automatically instantaneous unless I say otherwise, and acceleration is instantaneous unless I say otherwise.
Bless you. Thank you.
Recall that velocity is dx dt, or s, or whatever you use. Where this is an infinitesimally small change in time, and this is an infinitesimally small change in position.
Yeah.
So, in essence, that is instantaneous displacement.
Okay.
It's where are you relative to where you were a moment ago, as opposed to at the very beginning.
Okay.
Isn't it just in that the same direction as velocity?
Yes, and that's perfectly legitimate way to do it. There are some situations where you can come up with alternate answers, depending upon how you set up the problem. So if I move up and then down, at the peak, my velocity is 0. But the instantaneous displacement, it depends on how you're nitpicking what's actually happening there at the top. But yeah, them being in the same direction is definitely a legitimate way of doing it.
Okay. Cause I was like really overthinking it, I think.
has power to that, but. Is this gonna do something?
Sounds like a cooler booting up.
Alright, I got something here. Anything showing up there yet?
Yeah, it's starting.
Yeah.
Okay.
Oh, I see.
Alright. So I'm recording this, and this will officially have copyright issues as far as YouTube is concerned. But I found out if you use copyrighted material, they give credit to whoever material I've used, which is fine.
The Grand Tour. I watched this recently. There's like an episode where I think like Richard Hammond like slammed into a wall or something. It was great.
Alright. Doesn't Richard Hammond slam into a wall? I guess he wrecks a lot. Not
Yeah.
Slam into a wall.
Yeah.
Okay, congratulations, James. This
Oh, that looks
is
like the side of a.
the steepest bank circuit I've ever seen. And I'm not even at the steep bit of it yet.
78 degrees at the top, apparently.
Ah, what's your plan, mate?
Well, what I thought we'd do is put a speed trap at the end of this curve where it goes level again, and whoever achieves the highest speed through this banking is the winner.
Right. Can we have a bit of practice first?
Could I make a couple of modifications to my Aston?
Not if it's swapping it for a DB11.
I literally can't get any higher than this. And we're going to drive up there. We do, don't we, to go fastest?
If you go off the edge,
Yeah.
it's oblivion.
No, because the tree will stop as well. 60 miles an hour as I approach.
Hear that?
Whoa, big pothole there. The first corner. Already, I can tell it's very bumpy. Oh, steering's gone very weird.
The cars aren't ready for it every time.
Christ, there's a lot of me. It's bloody ridiculous. Look where you're going, you have to look up. That doesn't happen in cars. It's wrong.
It's like a snack bar up there.
Coming up to the second back turn. Christ. The bumps are so unnerving. Jesus. Apparently, some of them are so violent they can make the car jump 4 feet to the right. Oh shit, that was a big bump. Bottle,
Whoa. Jesus Christ, that's terrible.
Finally, the practice laps were over. Oh, Christ, this scary.
Supercharged.
The problem with going on a bank turn is there's nothing you can do. You can't slow down, you can't speed up. If anything goes wrong, you're a passenger. And because he was aware of that too, Squeaky Boy decided he didn't want to play anymore.
Yeah, well, my practice laps have told me one thing. I don't want to do it. I've just gone right off huge motoring accidents and right off them.
Having decided that he didn't want to buy the farm, he went off to buy a farmhouse instead. So it became a two-car shootout, and Asbo Man was the first to go.
Actually, I want to get one of those.
Concentrate, mate, concentrate. Give it some beanage. That's terrifying. Bumpy. Bumpy. It's made the windscreen wipers come off. sensation, I promise you.
Right, this is it. Let's see how fast I can make this thing go.
That supercharger is working.
I think that straight cut gears thing.
You don't hear it? I don't know though, because I don't hear any like lag at all. It sounds like
No, I'm saying, I think it's the gears. I think they're straight cut. That's why I had a motorcycle with straight cut gears. That's what it sounded.
you might be right.
That's one of the scariest things I've ever done in a
So
car.
why does it have a band?
Anyway, I have the numbers from the speed trap here, and Jeremy Clarkson,
Yeah.
you passed it at 89 miles an hour. Well done.
That is brave. You're brave.
And then, James May,
32.
you passed it at 93 miles an hour. James May has won a thing.
Oh my god. I bet if they would have smoothed up, what is it called? I don't know
What are
it's
you
called.
doing?
They would have smoothed it out. They would have gone faster.
The embankment.
Yeah. Bumps at high speeds are not fun.
No, I'm scared.
The main reason I showed that is we're gonna do a bank track problem. I've got a video with a bank track problem. We're gonna do a slightly different one. But it seems like every semester, there's some student who gets the bank track problem and doesn't know what a bank track is. That was a bank track. It's at an angle so that you can drive at faster speeds.
That's cool.
And I believe that's available on Netflix.
Amazon Prime Video.
Okay.
Isn't that,
That's right.
those are the same people from Top Gear, right?
Yeah.
Yeah, they, Jeremy Clarkson got fired,
Yeah.
or they all got fired,
I think.
Yep, their contract ended or something, they didn't continue the show.
and Amazon said, oh, yeah, we'll take it.
Oh,
Everyone loves Jeremy Clarkson.
He runs like a farm now. It's called like Diddley Squat or something.
All right, so. So they said we're at 78 degrees at the very top, and they weren't quite at the very top, so we'll just go with a bank angle of 70 degrees. And what I would like to know is the maximum and the minimum speed. Because if you go at a maximum speed, you'd start sliding up. If you go at a minimum speed, you would start sliding down. So basically I want to find the maximum and speeds. Now the video I do, I tell you the speed and I say what's the maximum angle and what's the minimum angle. This is sort of the reverse of that. The process is very similar. I do need to give one bit of important piece of information. Is that the static coefficient of friction between tire and
Asphalt?
asphalt, or if we want to do that one, concrete.
Oh. Tire?
And that is found by looking it up.
Oh, this is like a.
So coefficient. Helps if I spell. Yeah, they probably leave the R out. All right, wow. Coefficient of friction, rubber, and dry concrete. From 0.4 to 0.75 under what conditions?
So 0.4 if it wasn't one?
Yeah, this is odd wording here.
0.4, 0.75.
That makes them like dry or wet surface or something? Does that have anything to do with it?
I am assuming 0.45 is wet.
Yeah, because it's less friction if it's wet. So, yeah, it's 0.75? It was ground.
0.45 So we have a regular dry environment. Just to make sure I'm looking at the right thing here. Oh, I think this might be like driving through concrete.
Driving through concrete?
It's like concrete, it's friction, it's like concrete.
Could be some friction there.
Static coefficient of friction, rubber on concrete, 0.6. Don't know that.
Will we learn how to calculate that on our own at any point?
Yeah.
Is that like really high level?
Like, most problems, most static frictions are probably around the 0.4 range. It is possible to get above 1, but those are rare. And yeah, this is higher. Rubber on asphalt, I believe, is somewhere around 0.8 or so.
I meant like at any point in this course or future courses, will we know how to calculate that on our own? That value?
Would we? Here's how you do it. A use felt pad on table. Static coefficient is what keeps it in place. So right now, there's very little static friction involved. We're not at that breaking point yet. As I lift it farther and farther, more of the component of the weight is down the ramp. Because if it were completely vertical, the weight would be completely down the ramp. But as I go up and up, the static friction required to keep it in place is more and more. So it's getting close, we're having more and more static friction. We get to a certain point and there will be an angle at which it starts to slide. So somewhere around there. And you would measure the angle. So it's just a straight Boxell ramp problem, some angle theta. If I did a force diagram there, we have weight acting down. We have normal force acting this way and friction acting back that way. Static friction, because that's what we're looking for right now. I set up my coordinate system. Since officially it's not accelerating, I have more freedom with my coordinate system, but I want to minimize what I need to break up. If I set up my system like this, I hat, J hat, then I only have to break up one force. So I set it up like that, I break my weight up. So I have normal force this way, I have friction acting back this way, I have weight cosine theta acting this way, and weight sine theta acting that way. My equations of motion, I have W sine theta minus the static friction is equal to 0. It's static, it's not sliding. I have, and then for this one, y minus W cosine theta is equal to 0. Substitution, we have an independent formula for weight, we have an independent formula for friction. So this is mg sine theta minus my static friction. Because remember, static friction builds and builds and builds until you hit that breaking point. So static friction is less than or equal to mu sub s times the normal force, or the breaking point is when the static friction equals that maximum amount. And since we're looking at that breaking point, we'll be using mu sy here. And then y is equal to mg cosine. So plugging in the y value into the first equation, we get mg sine theta minus mu s mg cosine theta equals 0. And solve for mu sub s.
Oh, we can do that.
So in this simple type experiment, that's how you find use of S.
Okay.
And then to find use of K is you get it to slide and you figure out how long it went, you find the acceleration, and sort of work backwards to figure out what the force was applied.
Okay. This could all be circumvented by just looking it up.
Yeah.
Okay.
There's a certain side of my undergraduate degree is mechanical engineering, so, yeah, there is a certain amount of training of just looking up.
So if the value is greater than 1, would it be like it'd go past?
No, it just gets steeper and steeper.
Okay, so, okay.
Yeah, it can't hang upside down, if that's what you were picturing.
Well, it's like,
Is there
Velcro.
nothing that can stay in?
You would have to be sort of infinite to, if it were at perfectly 90 degrees.
Well, what would something like Velcro be?
See, I'm not quite sure that really counts as friction at that point.
No, yeah, it doesn't.
But
But it does beg the question.
Like, what about something like glue or, I mean, once again, does that count as friction?
I would, glue is an adhesion, there's something else going on there. Velcro to me is the same thing, you basically have a lot of hooks. You probably could come up with a coefficient of friction for Velcro, but is it really friction? Not the way I view it.
Maybe Velcro would be more like tension or anything.
Yeah, I think that's probably a more accurate way of looking at it. We will not deal with Velcro problems. Any other questions about this before I erase it and get back to this problem? All right, so we're gonna go through the exact same process as we have been doing.